disappointed a few people last month because we had a little bit of ice and snow that didn't get cleared, so we couldn't have the meeting, on the regular day. So that was kind of upsetting to a few people, their schedules anyway. So we're going to try to make up for it this time around. I guess we'll... Yeah, we're developing a setup for Zoom to have the meeting on Zoom in the future for those who can't attend, and also in case of an ice storm or tornadoes or something, we'll be able to still have a meeting of sorts. Yeah. Fires, yeah. Tsunamis, yes. Hey. Well, the way things are going, any of those could happen, And
all at the same time.
Yeah. One of those disaster movies, So I guess we'll start with Don here.
Hello, I'm Don Stevens, director here. Excuse me. Your cordial host. And, of course, I had to take this moment to have to start coughing, have a coughing fit. So we've resumed our Friday night programs. Those are most Fridays throughout the year. This time of year, they start at 8 p.m. In May, we switch to 9 p.m. Because of later sunsets. Then we take a brief hiatus summer with daytimes and switch to some daytime programs on Saturdays. Before resuming the nighttime programs in August. But check our website, they have our schedule there. And if folks want to, you got something you want to do, don't have anything to do on a Friday night, you want to come out and help out with those public programs, it's always appreciated. We can use help with parking or telescopes, stuff like that. You don't have to be necessarily an expert, just, come point at the moon or something like that, telescope for folks, and the public really appreciates it. We had a really good night last night. The weather turned out great for us after all. Even though they were promising clouds, it turned out to be clear. And we had a pretty good sized crowd, and it went really well. If you get a chance, come out and help us out and hang out and look through telescopes as well. I am going to, as I mentioned last month, organizing some telescope workshops that I will run a couple of times in the coming months for folks who just got telescopes, want to learn how to use them, how to care for them, stuff like that. My understanding is the club's going to do something similar in one of the meeting nights, but this could be a little bit more in depth and very special topics as well, care and maintenance, all that kind of stuff. There'll be 2 of those, and we do charge for those because it does take a lot to do these courses, and I do try to spend a little one-on-one time with everybody who attends those courses as well. The cost will be $90 for 2 sessions or both sessions. They'll be slightly different each session, different topics. Or just 1 session for $50, whichever one you're interested in. And I'll make the announcement once I have the dates firmed up on that. So probably going to be sometime in April is when I'm going to do those. So watch for that announcement. So I'll have someone post something in the club newsletter, and I'll also post on the email group as well. And if you're not on the email group, I recommend you joining it because I often post there for help, calls for help for programs, and say, we have to cancel or something like that. We often will send that out as email as well, so make sure at least the club has your email address if we do have to cancel a meeting or something like that, so you can be notified. And they've made arrangements to switch to Zoom, and I've over a couple months worth of work, we've managed to upgrade our internet here to wireless broadband, and so now we can actually do streaming from here during the meeting. So eventually the club will have that set up, and if you can't attend for some reason, at least you'd be able to watch the meeting over Zoom. So anyways, I got the new network up and running, and it's running smoothly and has good speed, so excited about that opportunity as well. So without further ado, I guess, here. Back over to Charles.
Oh, okay.
Charles,
Yeah.
real quick, folks, I have a sign-in sheet for folks who might be interested in joining us to help with the Friday night Perkins programs over here. If you're interested in any of the upcoming dates between now and the next meeting, just put down your name and email, and that way we can kind of keep the list. You can take this and we'll just run back.
Yeah, and if you do volunteer, you don't have to be a telescope expert or anything, because we're just sort of helping, manage the crowd and show people a few things through the telescope, look at the moon, and this right now, it's a pretty good time for that because you got Jupiter and Saturn and Venus and all the easy targets, that are nice things to show people that are just starting out, curious, whatever. So, anyway, we do need volunteers.
Yeah, we can also kind of suggest targets for you, so, if you can point a telescope at like the moon, you'll be a big help.
Yeah. Okay, so, guesses.
Greetings, hello everyone. Those who don't know me, I'm Isaac Cruz. I'm the head for CAS, the Columbus Astronomical Society Imaging SIG, Special Interest Group. And if you're interested in actually imaging, right, taking pictures of the of what is up there, of the cosmos, please talk to me, and we'll be more than happy to try to help you and steer you the correct way. Also, next Saturday, like the third Saturday of every month, we also have a CASIS meeting right here in this venue, and it's at 1 o'clock in the afternoon, and you're all cordially invited. So if you're curious about taking images, if you're, kind of like always thought about, taking your camera and pointing out to the sky and see what you actually get and what you need and basically all that it takes to start taking pictures, you don't have to be, definitely, you don't have to be an expert. On the contrary, I think that if you're not an expert, it's better, because that way you don't have any bad habits, and, I can kind of steer you kind of the right way. But either way, you're cordially invited for next week to come here. It would be February the 15th, and we'll make some other announcement, let's see, on February. Well, what we're going to do, because this is kind of the general meeting, well, I'm planning to actually do a course on PixInsight, which is the one and only image processing program that I actually kind of like feel comfortable with teaching. So we'll actually do that, and the plan is to actually do it in March. So it will be the same in March 14, 15, and 16. It's a 3-day course that we're going to put together, to actually put this together. And it will be probably about 12 hours worth of instruction altogether. So it also be charging about that, so I'll be making some announcements and some details in regards to that. But again, if you're interested, come on over next Saturday. You're here at 1 o'clock, and we can have some fun on imaging. And thank you.
Okay, so, first,
Yes. Hi, gang. Just wanted to let you know that the John Glenn Astronomy Park starts its programs back up on March 7th. That's the first Friday in March. If you'd like to help out, and if you don't come up here, I'd say come to Perkins first, and then John Glenn Astronomy Park second. We do have a good bank of volunteers, but if you want to join us, particularly on Saturdays, please feel free to come down. That is my one announcement. My second announcement here is last month people asked if I still had calendars for sale. I have exactly 4 left. If you'd like to buy one for me, they are $20. But because you guys are members of the Columbus Astronomical Society, they're $20. So, so
You charged us 25.
yeah. So I accept Venmo, cash, checks, fair trade, I don't know, Bitcoin. No, I don't do Bitcoin. No, not Bitcoin. But if you'd like them, they're going to be over here. And hit me up later. So, actually, I would run away if that were the case. So, but yeah, no Doge, no Doge.
So, we're almost ready for the program. So, last thing before our presentation, do we have any visitors tonight? No? Okay, well, then we will proceed with the program.
Okay, let me get started here. So, I've always been interested in relativity because it is so incredibly weird. So to give you guys, to give me an idea of what you guys know about it, would you guys shout out some of the things that you know, just generally, especially, about relativity? What do you know about relativity? Einstein, yes. Keep going. Spooky action at a distance. That's actually quantum theory. That's different than relativity, yes. Time slows up. I'm sorry? Time slows up. Time slows. That's a good one, yes. Anybody else? Yes. The inertial reference frame. That's something we're going to talk. Speed of light is a big deal. So all of those things minus the spooky action at a distance actually kind of comes into play here. My goal in this is to show you that contrary to what people might expect, special relativity, which is the particular version of relativity that Einstein published in 1905, is actually pretty simple mathematically. And to prove it, I'm actually going to do the math for you in front of you. Hopefully I'll be able to do it under the pressure of you guys standing here. The math is no more complicated than something that a senior in high school could do. It's actually very, very simple. So I'm going to go through and show you how the weird things of special relativity, some of the weird things in special relativity come about as a result of the mathematics. But first, I kind of want to, first of all, it's also weirder than you thought. First of all, who invented the concept of relativity? Yes? He knows. It's a trick question, yes. My goal was to get you to say Einstein. But actually, the person who invented the concept of relativity was Galileo. And the concept of relativity is a very simple one. It is simply the statement that no matter where you do an experiment, and no matter how fast you are moving, when you do an experiment, the experiment will come out the same for you. So if I get my chemistry set, and I'm standing on the surface of the Earth, and I mix a bunch of chemicals together, I'm going to get a certain result. And then if I get in a spaceship, and I fly at 99% the speed of light, relative to the Earth, and I do that same experiment, it's actually going to achieve the same result. Galileo made this proposition. He said later on in life, in 1632, when he was under house arrest, he was doing some interesting scientific experiments. He just came up with the idea that no matter what you do, experimentally, you can actually, your motion does not matter. So if you're, at those times, if you're on a boat or riding on a horse and you do a science experiment, it will actually come out the same as if you're standing on the ground. Now, Galileo didn't have spaceships or rockets, fast trains, or anything like that, but he was imagining in his mind the ability in the future of human beings to move very quickly. So he put it this way. He said, all experiments should give the same results no matter the velocity. Now, there's a really important thing, and this is where Don's future program comes in, and this is where Einstein actually divides relativity into two parts, the special relativity and general relativity. Special relativity is the relativity under circumstances where acceleration is not present. So if you are floating freely in space and nothing is happening, you're not actually accelerating, you're floating freely, this is what special relativity is all about. Now, we're standing here on the ground, we're experiencing a gravitational field, we are, in the general relativity sense, actually experiencing acceleration. So our experiments that we do here on Earth right now have a tiny general relativistic component to it. And so they are not 100% technically correct. But, the effect is very small. So when we do it when we think about these effects in special relativity, we can usually discount the general relativistic effects in practical terms. Let me make sure that this is actually pointing where I want it to point here. Give me a sec, thank you. So yeah, in other words, there isn't an experiment you can do to tell if you're moving or not. I mean, if it were the case that I could do a chemistry experiment and, the two chemicals mix together and I get a red solution, and then if I'm moving really fast, I get a blue solution, that would be a thing that would tell me if I'm actually moving through space. But there is no such experiment. There isn't an experiment that will tell you whether or not you are moving. Discounting acceleration, of course. So this actually came about, this was the general way of looking at the universe for quite some time. 1632 was when Galileo actually proposed this idea. It became kind of the way Isaac Newton looked at the universe when he did his mathematical framework. And in fact, Isaac Newton actually considered, when he mentally envisioned the universe, he envisioned the universe as a giant lattice with clocks at every intersection of that lattice. And all the clocks read exactly the same, off into infinity. That was Isaac Newton's way of looking at the universe. So there's an important concept to kind of go over to kind of get you started. And this is actually was one of Galileo's ideas. It's the concept of the inertial reference frame. An inertial reference frame is simply the state of motion that you are in. So I'm standing here on the Earth. My inertial reference frame is the same as the inertial reference frame of the Earth. If someone's flying in a rocket at a quarter of the speed of light past the Earth, they are in a different inertial reference frame. The Galilean proposition is that those two reference frames are equivalent, and you can actually transfer between those two simply by adding velocity to the one inertial frame to the other inertial frame. So you can actually change your experimental setup by simply adding velocity. Once you're up at that second velocity, the two experiments will work exactly the same. And by the way, a couple of these pictures, I just kind of wanted to give you an idea. This was befitting the idea that special relativity is kind of weird. I did a lot of these pictures with AI. This was actually done in Photoshop, and the prompt was a lattice of clocks going off into infinity. And this was the one that came up. And I said that are all on the same time. Okay, and do they look all on the same time? They're not actually all on the same time. It didn't come out right. But I'm showing you these because they're weird and funny, and that's what kind of came out. The science experiment, little chemistry experiment here, is also a little thing that I generated out of the blue in AI. The prompt was a lab full of computers, beakers, and chemistry experiments. And that's what it came up with. Yes?
Would you kindly explain inertial reference frames one more time? What was that definition you gave us?
The inertial reference frame is simply your state of motion. So it's simply the state of motion that you are in. And any inertial reference frame is equivalent to any other inertial reference frame, assuming that there's no acceleration. Yeah. So this is my no acceleration, no acceleration, yeah. So Galilean relativity actually works pretty well at low velocities. If you're dealing with the speed of cars or airplanes or even rockets to the moon, rocket to the moon might go 25,000 miles an hour when it leaves orbit. The effects of what we're going to talk about a little bit later are incredibly small. And so Galilean relativity, just adding one velocity to another and saying, yep, they're the same. If I look at the experiment from my point of view that's flying across in a rocket ship that's going 20,000 miles an hour, it's going to look the same to me as it does to the person inside of that rocket ship. So it's at low velocities, we can pretty much discount any of the special relativistic effects that we're going to learn about here. But there's a problem. And the problem comes about in the 19th century. And in the 19th century, people started to learn about the strange interaction between two common forces in nature that they were already familiar with: electricity and magnetism, which we actually jointly combine together nowadays as people who study physics into a single unit, electromagnetism. And over the first half of the 19th century, people began to discover the relationship between these two things. And this guy, James Clerk Maxwell, who was pronounced Clark, not Clerk, developed a series of equations that actually combine all of those principles together to tell you the relationship between electricity and magnetism. Let's go through those one at a time here so you can kind of understand them. First of all, the earliest one was Gauss's law, which basically just says, E, by the way, stands for electricity. Gauss's law basically says that if you got a charge, it's got a force coming off of it. And if you draw a circle around that charge, that force is always going to be the same no matter what force you have coming off of it. So if I take the entire series, a circle that's all the way around this, basically that's going to be one charge. And then if I get closer, it's still going to be one, but the lines are going to be closer together. And basically, the force of the electrical force acts a lot like gravity. I mean, if you've got a mass in space, something's going to go toward you because of gravity. Well, an electric charge, if you have something that's susceptible to an electric charge, like a charged object, it is going to be affected by an electric charge. Now, the weird thing about electric charges that gravity doesn't have is that electric charges come in two different flavors. We call them positive and negative. And if you've got a positive charge and you got a negative charge, the force is actually going to follow strange lines between the two of them. You're actually going to get this weird thing. And if you draw a circle around one or the other of these, you will still get one. But if you draw a circle around all of them, the two will blend into each other and you'll get zero force. So that's Gauss's law. Second law is just stating the nature of magnetism. Now, magnetism is kind of a little bit different than electricity. Magnetism also has a positive and a negative side, but you cannot split the positive and negative side from one another. There is no such thing as a positive side of magnetism without a negative side. So you're always going to have both of them. So if you draw a circle around around that, I forgot I had a pen here. Let's see. If you draw a circle around that, you will get 0, because some of the lines that come out of the positive side will bleed into the negative side, or vice versa. The lines will, if you draw a circle around the entire magnetic field, you will get 0 total force lines. Now, the next two laws actually talk a little bit about the relationship between electricity and magnetism. The first one, the Ampere Maxwell law, says that if you've got an electric charge that is moving, so this electric charge is moving like that. You know what? I'm going to do something here. So if you have a moving charge, a moving electric charge, it will actually generate a magnetic field. So if you run, I don't know if you guys have ever done this, if you take a battery, I wouldn't do this because you can actually burn yourself, but if you take a battery and you run a copper wire from one side of the battery to the other side of the battery, making a contact, and then if you twirl it up in circles to kind of increase the amount of magnetism, you can actually make an electromagnet out of this moving charge. The interesting thing about the moving charge is that it goes around it goes perpendicular to the motion of the charge. So here's the motion of the charge, and the magnetism goes around perpendicular to the motion of the charge. So you can actually use an electric charge, a moving electric charge, to generate a magnetic field. This is the basis of electromagnets. I don't know if you guys have seen those giant magnets that pull up car parts in junkyards. But what they're doing is they're taking a heck of a lot of electricity and they're running around a coil, and that's generating a magnetic field, and they are able to pick up a lot of junk, metallic junk, with the electric charge. And the final Maxwell law is Faraday's law, which is the inverse of that. If you have a moving magnetic field, the electric field, it will actually have an impact as if it were an electric field. So an electric charge, like a proton or a positron or an electron, will be affected by the motion of the magnet. And that acts a lot like the electric charge itself, like Gauss's law. So if you're moving a magnet through space, it will attract the appropriate charge toward the magnetic field. So all of these were ways to look at electromagnetism. And people thought they pretty much had it figured out. You know, they had a really good idea that this is how electromagnetism worked. Interestingly enough, if you want to figure out the speed of light, you can actually take these two empirically derived constants. One's called the vacuum magnetic permeability, and the other one is the electric vacuum permittivity. I never knew why one was permittivity and one was permeability, but that's just the way they call it. The relationship between those two actually is directly related to the speed of light. If those constants were different, the speed of light would be different. So this you can use these two to figure out the speed of light. And in fact, these two are empirically derived by simple experiment. You can figure out how much electric charge is generated by a moving magnetic field, which is the magnetic permeability, and you could figure out how much magnetic charge is generated by a moving electric field, which is the electric vacuum permittivity. And you can empirically derive that, and then there's a nice formula that you can get to get the speed of light. The speed of light is not just some weird thing that comes out of nowhere. It comes out of these constants in nature. Finally, short time after Maxwell published his equations, people started to figure out the consequence of these things. And a guy named Hendrik Lorentz, who comes up a little bit later in this talk, decided that he would kind of consolidate all of them into a model that showed you what happened to a charge given motion, an electric field, and a magnetic field. And it's simply this. The force, and Q always stands for charge in these things, equals Q times the electric field plus the velocity times the magnetic field. So if you've got a moving magnetic field, that actually adds a certain amount of force. A moving magnetic field, that actually adds a certain force on the charge. And if you just have a charge sitting there, an electric field, that also adds a force. If you've got both, then you've got a little bit of both. They actually add together. Is it good? Okay. So those two things together combine to produce the force that is felt on electrons and positrons and things like that are flying through space. And this is actually this is that equation, by the way, right there. That equation, this is the relationship between the electric permeability and the magnetic permittivity. This is how you derive the speed of light. This is a picture, an imaginative picture showing the speed of, showing actually what happens to an electric field and a magnetic field to generate a beam of light. So what happens is, we'll say that up and down is the electric field, that's E, and then side to side is the magnetic field, which is B. So as the electric field goes up, the magnetic field goes up. And as the electric field goes down, the magnetic field comes back down. The magnetic field overshoots, and it generates the electric field. So what happens is one generates the other, and the two progress through space. This is how the speed of light works. So in the 19th century, yeah, they're perpendicular to one another. They come out perpendicular to one another. That is correct. So in the 19th century, people had this idea based on their experience with other types of waves in water, waves in air that produce sound and that kind of thing. There was the idea that if you had a wave, like a beam of light, that it had to actually go through something. A wave has to have a medium with which to wave. And this particular medium kind of had a weird property. I call it the cosmic honey. And the reason why I call it the cosmic honey is because they considered that the speed of light was limited by the kind of stickiness of this material.
Talking about the ether, right?
Yes, I'm getting to that, the ether, exactly. But what's weird is if you did other experiments about motion and that kind of thing, you took other fields, you would have to have a different viscosity for each of the honey, And they called that, they called that the luminiferous ether. So my luminiferous ether is a honey-colored water there. So they had the idea that the waves were moving relative to a fixed stationary luminiferous ether, is what they called it, that permeated all of space in every direction. So if you had a light beam, it moved at the speed of light through the luminiferous ether. And just for fun, I decided to put into my image generating software the word luminiferous ether, And this is what it came up with. AI is very strange, you know. Okay.
I don't think it was trained correctly for that.
Yeah, it wasn't trained. Yeah, I mean, it's trained for, you know, business meeting, handshake, that kind of thing. So, right around this time, maybe, you know, 20, 30 years after Maxwell's equations and Lorenz's summation of the forces on moving charges, there was a young man who spent a little time bicycling around the backwoods of Tuscany. And this particular young man would engage in what he liked to call Gedanken experiments, which in German I learned means thought experiment. Yes, an experiment in your brain. And one of the things he thought about was what it would be like if in this luminiferous ether-filled universe, you could actually travel along with a beam of light. Now, if I'm traveling along with a beam of light, I want you to think about this. If I'm traveling along with a beam of light and the magnetic field of a charge, or the magnetic field that is generated by a moving charge, is actually seen to be moving along with me, I will actually see no motion. And because I see no motion, what the Maxwell-Ampere law says is that I won't see a magnetic field. So in other words, if I'm moving along with a beam of light, the beam of light disappears. And this is clearly not, and if I'm moving a little bit less than the speed of light, the beam of light gets kind of weak and doesn't really do what we expect it to do. You know, the magnetic field is moving a little bit relative to us, and so it's extremely weak. Oh, and the speed of light would also change. You know, those two magnetic permeability and electric permittivity, those two would actually result in a speed of light that is much lower. Now, this is clearly not what's happening. Let me explain to you what's going on. By the way, I had my AI was Albert Einstein riding a bicycle in Tuscany. This is what it came up with. That doesn't look like Albert Einstein. So I put a young Albert Einstein on the head there. Then I also had Albert Einstein riding a beam of light. That is a scary-looking Albert Einstein. It's Albert Einstein is like a zombie or something like that. But I thought it was kind of cool because he's surfing. You know? Yeah, he's terrifying. He's really awful. So this is a example that I got out of Richard Feynman's lectures, which he's a good explainer of physics. And I want you to imagine a different scenario in which we have, and this is my invention, the electric chipmunk, and a wire filled with positive charges and negative charges. And if you have a wire and there's no current running through it, you have an equal number of positive charges and negative charges. So the electric chipmunk here does not feel a force toward the wire because there's no current. There's no magnetic field or electric field around the wire because the positive and the negative charges cancel each other out. It's zero. One of them cancels the other out. So if you set everything in motion, what ends up happening is that the charges are now moving through the luminiferous ether. And you end up with a magnetic field being generated if the charges are in fact moving. And our electric chipmunk starts to move toward the wire because of the induced magnetic field that came about as a result of that. But if you look at that motion from the electric chipmunk's point of view, there is no motion. So let's imagine that the electric chipmunk is moving along at the same speed as the wires, as the electrons in the wire. There's no motion, and so from the point of view of the electric chipmunk, we don't get any magnetic field generated, and so there is no motion. So the two of them are disagreeing with one another. This is a very weird problem. I mean, this is something that people in the 19th century hadn't yet kind of got a grasp on. One of the things was that guy Lorentz that we're talking about decided that if a charge is moving through the luminiferous ether, what ends up happening is that the charge actually ends up getting squished a little bit, which is kind of right, but it doesn't take the last step. So let's take a look at the solution to this particular problem. And the solution came about as a result of this paper. This is the English translation. I couldn't find a picture of the front page of the actual German. This is on the electrodynamics of moving bodies. And in the very first sentence, in the very first page on that, I think it's, let me see, it's, okay, it said, it is known that Maxwell's electrodynamics, as usually understood at the present time, when applied to moving bodies, leads to asymmetries which do not appear to be inherent in the phenomenon. In other words, asymmetries means if you do one thing, you get one result. If you do another thing, you get a different result. And to be inherent in the phenomenon means, hey, when we do experiments, we're getting, what Maxwell's equations are showing us in the luminiferous ether is not what we're seeing. Well, Einstein actually, came about this simply by his Gedanken experiment. He actually thought about how the Gedanken experiment, he actually thought about how this would work in the Maxwell's equations. And he decided that he would actually take the idea of relativity from Galileo and take it one step further. He would actually throw out the idea of the luminiferous ether. He basically said, okay, let's assume that there is no medium through which the universe, which electromagnetic waves propagate through the universe, and let's take and make two propositions. Number one is basically Galileo's proposition. The laws of physics are the same in all inertial reference frames. We already got that one down. That's Galileo. But the other one, which is kind of dramatic here, is that the speed of light is the same in all inertial reference frames. So let's just assume that the speed of light is the same in all reference frames. Now, there was an experiment that seemed to indicate this, that Einstein could have known about. He claims that he did not factor this into his Gedanken experiment. But that experiment that he did not know about or did not reference when he was coming up with this was something called the Michelson-Morley experiment. And the Michelson-Morley experiment was basically just a set of mirrors and a light beam, and what would happen is the mirror, they'd actually fire a beam of light out here, and one beam of light would go reflecting off. It would actually split the beam of light, and so one part of the beam of light would go out here, the other part of the beam of light would go here. And then it would reflect back like this and come back together, and then they would actually read the result and that little thing right there. And they could actually calibrate this so that when they fired off a beam of light, they would pick one particular frequency. They would usually energize a little gas, some hydrogen or something like that, and it would produce one particular frequency of light that was very collimated. And they could adjust the distances here so that when they fired off the beam of light to both of them and they came back, you could actually make the light disappear because one light beam would cancel out the other. The two would actually result in no light seen at all. And what they did was they conducted an experiment over the course of an entire day. Now, I want you guys to visualize what happens if you're standing on the Earth during the course of a day. So, let's imagine you're standing on the Earth and you're watching the sun come up. So as you're standing on the Earth watching the sun come up, you're actually moving perpendicular to the sun through space. You're moving up in your direction, from your point of view. Now, 6 hours later, when the sun gets up here, the entire Earth has turned. And so now what's happening is you're moving off in this direction, over here. Now, if you did this experiment 2 times, 6 hours apart, at one point you would actually be moving, and let's assume that there is a luminiferous ether in the universe. At one point, you would be moving one direction through the luminiferous ether, and at another point, you would be moving a different direction through the luminiferous ether. So if the luminiferous ether had its own preferred fixed point in space, if it had its own fixed point in space, you would actually get 2 different results. So here I'm moving, when the sun comes up, I'm moving this way, and when the sun is up high in the sky over here, I'm moving this way. It's going to give me 2 different results. And you would actually be able to see those beams of light get a little bit out of phase. Because what would happen would be when you're moving into the luminiferous ether, according to the 19th century conception of things, the speed of light would slow down in that direction. But if you're moving along with it, maybe perpendicular to that, it wouldn't slow down. You would actually get a faster speed. And so the result of the Michelson-Morley experiment would be different according to which time of day you were actually conducting it. The thing is, this was a failed experiment. No one was able to see that the speed of light was different depending on which direction you actually looked. This is actually the chart that shows that, and these lines here are what they expected, and this here is a very rough estimate of what they measure the speed of light is. There's a little bit of noise coming. There's a little bit down here. There's a little bit up. You think, okay, well, maybe something's happening. Well, here's the thing. They calibrated this particular chart so that this sine wave here, which is what they expected as the Earth turned, is actually 1/8 the size that they wanted it to be. They just needed to bring it down into the paper. So the result is negligible compared to, so what they're getting is they're getting something like that, or something that goes way off the top of the chart there. So in other words, the Michelson-Morley experiment, other than a little bit of noise, gave a null result. The speed of light, according to the Michelson-Morley experiment, was the same in every direction. So I could be moving, in a spaceship, I'm going really fast around the sun, 66,000 miles an hour roughly. It's about how fast we're going around the sun. And then we're not going 66,000 miles an hour over the sun. We're going a different direction, in a different direction. So that even that big difference in direction through the luminiferous ether could not be detected. Einstein didn't need that. But it was nevertheless there. It's a piece of evidence that actually demonstrates his second postulate, which is the speed of light is the same for all observers. So you could move as fast as you want, and the speed of light will be the same in all directions. Einstein didn't take that experiment. He just said, let's just assume that it is, and let's see what happens. So let's do that. So here's where I'm actually going to do a little bit of math here. This is his Gedanken experiment. Slightly modified, he used trains. I like to use spaceships because we're spacey people. So let's imagine we're standing here on the Earth. I need two names. I need a name for the person on the Earth. Give me a name. Jeffrey. Okay, and now I need a name for the person in the spaceship. Charles. Okay, so we got Jeffrey. So this is Jay. And now we got Charles here in the spaceship going on. Can you guys see that? Or maybe I could turn off the light here. Let's see. Okay. So we got Jeffrey and Charles.
Let's turn the backlight back on.
Okay. Let's try that. Is that good? Okay, we're good. Okay, so Jeffrey and Charles have a very strange apparatus. Jeffrey is standing down here on the Earth. Let's just assume that the Earth is not spinning, it's fixed. And the spaceship is flying through space. And on the spaceship, Charles has got this strange clock. And the way this clock works is that you fire a beam of light between two mirrors, and they bounce up and down. The light actually bounces up and down, bounces up and down. Now, if the two are in the same inertial reference frame, let's say the spaceship is far enough away that it's not falling toward the Earth very much, and Jeffrey is standing down here on a motionless Earth. We're doing special relativity, so we're not accelerating. We're discounting gravity and all that kind of stuff. So let's say that the time for a photon to move through from one mirror to the other, let's just, for simplicity's sake, let's just call that 1 second. We can make a second a little teeny, like nanosecond or something like that. We can make it a real teeny amount, but let's just say 1 second just to kind of make it a little bit easier. So if Jeffrey and Charles were standing and looking at this experiment being conducted on the spaceship, every second they would see the photon of light hit a mirror and bounce back and forth. So 1 second would pass for Charles at the same time, at the same rate that 1 second would pass for Jeffrey down here on the ground. So the time that the photon takes to get between one mirror and the other is t, that's the time, or the amount of distance that the photon travels during that time is t j times c. T is time, and this is tj. This means the time according to the point of view, the stopwatch of Jeffrey. So that's tj times c. You guys get that? The math is pretty simple so far. So, but if you have a different circumstance and the spacecraft is moving, we've got Jeffrey down here on the ground. My art is terrible. And then we've got Charles moving really fast in the spaceship. From the point of view of Jeffrey, the photon of light is going to be moving a zigzag pattern. And here's the problem. According to Einstein, the speed of light is the same in every reference frame. So, from the point of view of Charles here, the light beam is doing that. It's going up and down. But from the point of view of Jeffrey, it's actually going at this zigzag direction. And you'll notice that each time it reaches the other mirror, it's actually traveled a lot further than it does between these. Now, how can that be? The speed of light, from the point of view of Jeffrey, is actually going faster for Charles's spaceship. Einstein said, no. That's not what's happening. That's not what's happening. Something very strange and weird is going on. So let's take a look and figure out the math that Einstein used to figure out what's really happening. And I'm going to have to show you a couple of very simple pieces of math. This is actually a picture to show you the converse. From the point of view, we're following Charles in the spaceship. From the point of view of Charles, Jeffrey's light beam going back and forth. If the Jeffrey had the same experiment on the ground, Jeffrey would actually see the speed of light be a lot faster if this one weird thing that Einstein postulated didn't occur. So Jeffrey, from his point of view, is seeing this, but from Charles's point of view, the Earth goes flying by. I put a little motion blur on my picture there. The speed of light is actually increasing. Remember the postulate. Speed of light is the same in all inertial reference frames. The Michelson-Morley experiment proves that. So I want to remind you of a few. Do you guys remember your high school algebra? Anybody? Who's like terrible at math? Fess up. Okay. If you're terrible at math, who kind of does math pretty well? Okay. So I'm going to remind you of a couple mathematical things here. So a really important thing is the square root. You guys know what the square root is. The square root of a number is the number that you multiply by itself to get another number. So the square root of x is, whatever you multiply by itself to get x. So if you have the square root of two numbers that are multiplied together, square root of xy, mathematically that's the equivalent of the square root of x times the square root of y. Those two, those are the same thing. The opposite happens too. So if you have xy squared, my handwriting is terrible, I'm sorry. That's the same thing, oops, excuse me. Yeah, that's the same thing as xy squared. Okay. So if you take the two of them, you take y squared times x squared, it's the same thing as x times y squared.
You need parentheses. Yeah, you need parentheses.
Oh, that's, yeah, so yeah, you kind of do that. Oh, xy squared. Okay. I'm just assuming they're stuck together. So yeah, okay. So, and then finally, we need a very simple mathematical relationship called the Pythagorean theorem. So here's the Pythagorean theorem. If you have, yes, A, B, and C. If you have a right triangle with sides A, B, and C, if you take a squared and add it to b squared, you will get c squared. This little box right here means it's a right triangle. That means one of the angles is 90 degrees. That's all it means. This is all the math that you need. Maybe a couple of extra, like canceling things out and that kind of thing. But really, the math for special relativity doesn't get much more complicated than this, unless you're getting into some of the really weird stuff. But we're going to deal with the weird effects on time and distance and that kind of thing with that experiment here. We are going to start with our spaceship, and we're going to imagine, what was it? It was Charles in the spaceship and Jeffrey down here. And here's Jeffrey. And we're going to imagine that the spaceship is moving in this direction. It is moving at a velocity v. That's the velocity. Let me get rid of that. Here, boop. There. We're going to go. It's moving at a velocity v. And the velocity v. The beam of light is actually moving between the two mirrors like this. So from the point of view, like we saw before, I'm going to make the beam of light yellow this time. From the point of view of Jeffrey, the beam of light is going here, it hits the mirror, comes down here, hits the mirror, comes up here, hits the mirror, comes down here, hits the mirror. So let's imagine from the point of view of Jeffrey, what would happen if the speed of light were in fact constant in Jeffrey's point of view, right here. So if Jeffrey had the same experiment here, his measurement of, so this would be the amount of time that it takes times the speed of light from the point of view of Jeffrey. So if we want to say that, let's imagine that we're trying to figure out how far this beam of light gets from the point of view of Jeffrey on this. So let me go to my next thing. I'm going to actually draw this here. And here's my little rectangle here. And so let's say that this is the speed of light times the time that Jeffrey measures the light to bounce between the mirrors on his experiment. The speed of light is the same, however, when he watches the spaceship go by. So if we take this line and we bend it down so that this line and this line are the same, so this little part is CTJ, like that. That's the same thing. We want to figure out how far Charles would see the speed of the beam, how far we would actually see the beam of light travel toward the mirror to Charles. Here's the mirror up here. Here's how far the beam of light traveled to get to the mirror. So this is the time Charles, and this is the times c. Sorry, let me back up here. Let me do this over again. Sorry, I've never done this in front of an audience. I did it like 5 times just to get ready. So let's do this, and this here, C, T, J. Jeffrey's the guy on the ground, and this is C, T, J also. And this is C, T, Charles. Okay, so that's not what Charles would see, but how far we would see the light progress from the point of view of Jeffrey. And this, V, this is actually V times, this here is V times T in the point of view of Jeffrey. So down here we have the velocity times the amount of time that you travel from the point of view of Jeffrey. So we know the Pythagorean theorem takes these and squares them. So what we've got, and I'm going to try to write it really neatly, is CT J squared equals VTJ squared plus CT Charles squared. So this is just the Pythagorean theorem. So I've just taken and squared this side right here, which is, as you remember, it's this, but we've taken, this is the same speed as this, but it's just moving diagonally. This is how far it moved between the mirrors. So it's going to take, what's going to happen is the light beam is actually going to take a little bit longer to get up to the mirror from the point of view of Jeffrey down on the ground. It's actually going to travel 1 tick, 1 second, and then it's going to go a little bit further. So what's going to happen is from the point of view of Jeffrey on the ground, the moving spaceship is going to slow down. The clock of the moving spaceship is actually going to travel more slowly because it takes the light a little bit longer to get there. Let's see how long that is. So I'm going to go to the next thing. Oh, by the way, show your work is what my physics teacher always said. So I always had to, when I was studying physics, I always had to write everything down. So I've done this before. It's just been 30-something years since I studied physics. So we've got c t j squared plus v, oh, whoops, excuse me, go back, equals v t j plus c t c. Oh, squared. Yeah. Okay. Yeah. So these two are in parentheses. Yeah. When you put two numbers together, it's assumed that they're together. So I can actually put these in parentheses there. So let's solve for this. What do we want to solve for? Well, what we want to solve for is how much longer that light beam is going to take to get between the mirrors from the point of view of Jeffrey on the ground. So we want to figure out the ratio of the two. We want to figure out the ratio of TC to TJ. So let's try to solve for that. So first of all, what we need to do is just split everything up. So let's go c squared times t squared j equals v squared times tj squared plus c squared times t squared c. Okay, so let's take and we will try to figure out what we need to do here. Well, so first of all, we want to get this. So we want to get this over on the other side. So what I want to do is I want to take and subtract this from this. So I'm going to go c squared t squared j minus v squared t j squared equals c squared t squared c. Okay. So now let's see if I can actually erase that. Let's go on to the next page here. C squared, okay, hold on, let me go back. There we go. C squared t squared j, okay, t squared, yeah, c squared t squared j minus v squared t squared j equals c squared t squared c.
T squared, t squared, t squared.
Thank you. There we go. Thank you. Okay, so c squared t squared t. Okay, so what I'm going to do is I'm going to divide both sides by c squared. Actually, first of all, what I'll do is I'll take this and I'll pull out the t squared j squared. So I can actually take these guys out. I can go t squared j times c squared minus v squared, like that. So I can actually take these two out, equals this up here. So now let me divide both sides by c squared. So if I take c squared out here, what I end up with is 1 minus v squared over c squared, t squared j equals t squared c. We're getting closer. So this is you're starting to see something that looks interesting. Let's take this part here and divide the whole thing by it. Okay, so I'm going to take that. Oops, hold on. I'm going to divide the whole thing by that, t squared j, and I just get rid of that. Okay, so this is 1 minus v squared over t squared. Let me see if I can erase this. Hold on. I'm going to go here, and I'm going to go back and play. Yeah, there we go. So we are at this point, we have 1 minus v squared over, v squared over c squared equals t squared c over t squared j. Remember, t squared c is how far the light seemed to progress from one mirror to the other on the spaceship from the point of view of Jeffrey. And t squared j is one unit of one tick of the clock from the point of view of Jeffrey. Okay, this is squared. This whole thing on this side is squared. So let's take a square root of that, and we'll take a square root of that. So we end up with the square root of 1 minus v squared over c squared equals t c over t j, like that. So what we have is the relationship between how far the light beam on the spaceship seemed to move from one mirror to the other, from this one here, to how far it moves on the ground. Basically, we're seeing how much time has passed from the point of view of Jeffrey on the ground on the spaceship. But what we want is how much, just to be convenient, we want how much longer it will take that diagonal light beam to get up, that diagonal light beam to get from one mirror to the other. How much longer it will get. So what we need to do is we actually need to invert this. And if you invert one side, you have to invert the other. And a really easy way to invert one side that doesn't have any, it's not a fraction. So I'm just going to get rid of that, and this is j here, and this is c here, and all I need to do is go 1, like that. So this right here is what we've been going for. And just to make it a little clearer, I'm actually going to put it on a nice, clear, not bad handwriting value. This particular value crops up all the time in special relativity. They call it gamma. So if you want to figure out how much longer it takes from the point of view of Jeffrey, that spaceship, and here's my little flames. Come on. There we go. Here's my spaceship. How much longer it takes the light beam to get from one end of the spaceship to the other. From the point of view of Jeffrey, in one tick it only goes this far. It takes a little bit longer to get that far. Gamma tells you what you have to multiply this by to get this. So let's take a look at this equation just very simply. If you have the velocity very close to 0 relative to the speed of light, this whole thing is 0 over the c is the speed of light. So this is very close to 0. What's the square root? So what we're left with is the square root of 1. What is the square root of 1? 1, right. So if the velocity is very close to 0, 0, 1, percent the speed of light. Oh, come on. If it's very close to the speed of light, then this doesn't come into play. The v squared over c squared actually doesn't come into play. However, let me erase this. Give me just a second. There we go. And I will play again. However, if this gets very close to 1, let's say 0.9999, that kind of thing, really, really fast, then 1 minus 0.9999 is really, really big. Or it's very, very small, excuse me. So we get 0.000001 or something like that. So what's the square root of 0.000001? It's really small. It's very small. So we get 1 over something small. Well, 1 over something a lot smaller than 1 is bigger than 1. It's a lot bigger. So as we get closer and closer for the velocity being close to the speed of light, then this value of gamma gets bigger and bigger and bigger. So what ends up happening is, from the point of view of Jeffrey standing on the ground watching the spaceship go by, it takes longer for that beam of light to get between one mirror and the other. You've got something like this, very slow and shallow. You've got a very slow and shallow. Is that still going? Okay. You got a very slow and shallow type of thing. This situation where the speed of light is a very good percentage of, or the speed of the spacecraft is a very good percentage of the speed of light, is actually a situation in which the beam of light from here to here will take a lot longer to move from one side to the other, one side of one mirror to the other mirror as it travels through space. Now, conversely, from the point of view of Charles on the spaceship, if Jeffrey's doing the same experiment, he's going to see the same thing because the spaceship, the Earth is going to be going by. What's nice about this whole thing is it doesn't matter. If I'm standing on the spaceship, the experiments work. I'm going to see the speed of light on the Earth to be exactly the same. So what happens from the point of view of Jeffrey on the ground? Let's say, from the point of view of Jeffrey on the ground, that's the worst stick figure I've ever seen. Very nerve-wracking to do this. So from the point of view of Jeffrey on the ground, time actually seems to go slower for the spacecraft. Well, it not only seems to go slower, it is, in fact, from the point of view of Jeffrey, going slower. There is nothing you could do to change that. Jeffrey is always going to see the moving spacecraft's clock run more slowly. Anything that you do, if they did a chemistry experiment, which took 5 seconds to make a beautiful red color appear when you mix the chemicals, it's still going to, it takes a longer period of time for that to happen if the spaceship is moving at an appreciable percentage of the speed of light. So time actually does slow down. It's not just in clocks. It's not just in things that involve the speed of light. It is anything. You age more slowly. However, on the spaceship, it doesn't seem like anything is amiss. The world is not moving more slowly. And this is what is known as time dilation. And it is probably the strangest outgrowth of special relativity. And it comes simply from making two assumptions, or two postulates. Number one, the speed of light is the same in all inertial reference frame. And number two, any experiment that you do can't tell you whether or not you are moving or not moving. Those two postulates. So let's see some of the results of this. First of all, this is a plot of gamma versus the speed relative to the speed of light. This is down here at the bottom. This is V over C right there. That's the speed of light, the speed over the speed of light. So right here we've got 0.9% the speed of light, and we go up here. Gamma is something like 2 1/3 or something like that. If we go to 0.99 or 95, gamma gets up to like 4. So if you go up to 0.95, if I wrote the chart correctly, or 0.97-ish, gamma is about 4. So time appears to slow down 4 times for Jeffrey on the ground in the spaceship, if the spaceship is going 0.97% the speed of light. It's going about 2.5 times slower if the spaceship is moving at 0.9% the speed of light. So you have to go pretty fast for time to slow down a lot. However, this doesn't stop here. It actually goes on to infinity as you get closer and closer and closer and closer and closer to the speed of light. This goes up, 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 up. Now, there's an interesting thought experiment that you can do. Let's say you're watching the spaceship fly through space, and it goes through a tunnel. And from your point of view down here on the ground, the beginning, we're taking a train here as our example. From our point of view on the ground, the front of the train takes a certain amount of time to go, from the front of the train being in the tunnel to the back of the train being in the tunnel. Now here's the thing. From the point of view of somebody down here, we've got Jeffrey down here watching this whole thing. This is Jeffrey, and this is Charles on the train. From the point of view of Jeffrey watching the spaceship or the train go through the tunnel, for this cart, for this train, time has actually slowed down from the point of view of Jeffrey. So how is it, if time has slowed down, how is it that the beginning, the entry of the train and the end of the train will be seen the same from Charles's point of view and from Jeffrey's point of view? Something weird's happening. So if time has actually slowed down from the point of view of Jeffrey on the train, what ends up happening is that this won't get through the whole tunnel by the time it moves a certain distance, by the time it moves the distance that it would ordinarily take. However, Charles would disagree. Charles would say that the whole train gets through at the same. The whole train actually gets through the tunnel during that same allotted amount of time. So what's happening? Well, what's happening is the other weird effect of special relativity. It turns out that in order to bring things back into alignment, the train or the spaceship or whatever it is actually gets shorter, squeezes together in the direction of motion. So that actually makes it so that the entire train, from the point of view of Jeffrey, can get into the tunnel in the allotted amount of time, and that Charles will see the train get through in his inertial reference frame. So this results in another weird effect of special relativity, which is called length contraction. Length contraction happens according to gamma. It's exactly the same. So if you want to know how much length something has squished, just divide by gamma. So at 0.9% the speed of light, 0.9 c, the length of the train is divided by whatever this is, 2.5 or so. So the length is actually a little bit shorter. So this is why length contraction occurs. Length contraction actually occurs because of the disjoint between Jeffrey's point of view and Charles's point of view. So that's one of the things. So the other effect here, let me see if I can go. So length contraction also goes according to gamma. So this is length contraction in Earth's reference frame. So let's imagine Jeffrey down here. This is, I keep hitting the forward button. This is Jeffrey, and this is Charles. So Charles is not a little c, Charles is more like that, a little squished up c as he moves through space. Now the same thing, here's the opposite effect. From the point of view of Charles, the Earth is length contraction. And so we've got, I'm going to try to draw this really skinny. This is This is our Jeffrey down here on the ground, and Charles is normal. So Charles is perfectly normal. So it all depends. From the point of view of the spacecraft, Earth squishes up. And this has actually been observed in experiments to happen. So this actually solves the problem that we had earlier, in which a moving charge seemed to not work with the luminiferous ether. The charge seemed to disappear when a luminiferous ether existed, and you're moving along with it. So let's watch what happens. Let's go back to our electric squirrel. And when you've got the electric squirrel next to a situation, next to a wire where the electric charges are not moving, then nothing happens. You're not getting a magnetic field because there's no motion. However, if it starts to move, then you actually get an induced field, and the electric squirrel starts to be attracted to the moving charge. These are all the charges moving along the wire. But here's the thing. What happens if the squirrel is moving along with the charges? So here's the motion of the charges, and here's the motion of the squirrel. Now, I cheated a little bit here. When we talk about a moving charge in a wire, the only thing that moves are the negative charges. Those are the electrons. They move through the wire. The positive charges, we generally consider those to be the protons, but what it really is the opposite of the electric charges. If you've got an electric charge flying through free space, and you have a bunch of them, if you have a space where there is no electric charge, that area is actually positive by comparison to the actual field of electric charges. So this doesn't have to be this up here doesn't have to actually be protons. In this case, it is. But let's see what happens. So if the electric chipmunk, is moving along with the electric charges are not moving, we still get a motion toward the wire. Well, what's happening? What's happening is that we're not getting a magnetic field anymore because the charges aren't moving. We're not getting a magnetic field. That's not it. So let's go back. What we're getting is length contraction of the positive charges. The positive charges, from the point of view of the moving squirrel or the moving chipmunk, are actually squishing together. So instead of getting a magnetic field, we actually get the opposite electric field. So we've got a positive charge. This electric squirrel, by the way, I forgot to say, this is actually negative. This positive charge is a slight length contraction of all the positive charges in the wire, and the density of positive charges is slightly more than negative charges, and so we end up with a slight positive charge to the wire, and the squirrel is attracted to the wire by an electric field and not a magnetic field. So what's happened? As the squirrel or the chipmunk moves faster and faster relative to the charges, the magnetic field slowly morphs into an electric field. You can get both. If the chipmunk is not moving as fast as the charges, You can get half magnetic field, half electric field. It's a very complicated equation that actually tells you how strong the force is. But from the point of view of someone outside of this watching, the chipmunk is always going to be attracted to the wire. So the problem with the luminiferous ether is solved by the length contraction that results in the positive charges. Now, Einstein, when he wrote his famous paper in 1905, it was called On the Electrodynamics of Moving Bodies. This is the problem that he solved. This is what he was working out. He was working out why do you get the same effect when you're moving along with the moving charges as when the moving charges themselves are moving and you're staying put? Why is it the same thing? And this is the reason why. Because of this length contraction. That's what the paper was about. And all of these other things, these weird outgrowths, time dilation, length contraction, there's another one that I haven't talked about yet, which is mass goes up. Anyone want to care to guess how much mass goes up as you get higher and higher? Gamma, exactly. It goes up with respect to gamma. Relativistic mass is just gamma. So if I want to take the mass, here's the mass. I just multiply my rest mass. They always call that with m naught. They always say that. The rest mass times gamma is how much heavier something is relative to you. I'm not going to derive that because it's actually a little more complicated. It involves things like Taylor series, and so that's a little too complicated. And you saw how much trouble I just had with it right now. So here's gamma as it goes up. So as you get faster and faster, your mass actually goes up. That's another weird effect. And there's a lovely effect that us who are interested in space can actually take advantage of, or at least in our minds. This gives us the ability to travel to the stars. Anybody know what this is? What is this? It is a Bussard ramjet, yes. It's a hypothetical spacecraft that scoops up the hydrogen in interstellar space and fuses it and creates a propulsion using that. Now, it's a proposed idea for traveling to the stars. So if you've got time dilation, let's say you want to travel to a nearby star system. You found a lovely M-class world 40 light years away. Now, we human beings, we don't live very long, and a 40-year trip is going to be a real pain in the butt. We'd have to take a lot of food. We'd get really bored. It would be very difficult for a group of people to travel for 40 years. So why don't we take advantage of time dilation? Let's make the time in the spacecraft slow down. And so we would be able to travel to the stars a little more quickly. So if we have a gamma of 10, we'd actually be cutting the time that it takes to get from point A to point B by a factor of 10. So we take 40 years down to 4 years. Now, at this moment, 4 years might seem like a very, very long period of time. But let's just say, for hypothetical sake, that 4 years is not a long time. We're getting to that star in ship time, 40 years, if gamma is 10. So let's figure out what it would take to get gamma up to 10. So first of all, in order to get gamma, in order to get that equation to read 10, the velocity would have to be 0.995% the speed of light. That's more than 99% the speed of light, 99.5% the speed of light. So that's pretty darn fast. That's really close to the speed of light. So let's figure out how much energy it would take to do that. Hi, this is Brad cutting in here just for a second. I just wanted to clarify something here. I made a mistake during the presentation. I added in the classical kinetic energy equation to the relativistic energy equation. It had been written in the textbook that I was referring to as an adjustment to the classical, but it's not actually an adjustment. It's a replacement for the classical energy equation. So ignore the classical part of the equation that I'm talking about right now and just take the relativistic part. I will not cut the video out so you can watch the whole thing. But the good news is that the classical part doesn't actually add very much to the relativistic part at this speed, so it doesn't make too much of a difference. But back to the talk. I'm going to do another little math thing. I'm not going to do it with my pen. I'm actually just going to show you it. This right here is the equation for the energy that a moving body has. It's called kinetic energy, KE, kinetic energy. Now, when we do an experiment in high school and we try to figure out, a 1 pound mass is moving at 1 meter per second, what is its kinetic energy? In fact, a 1 pound mass moving at 1 meter per second, it has an energy of 1 joule. Yes. So that is the unit that they use, that particular thing. But kinetic energy, when you get up to relativistic speeds, is different. First of all, because the mass of the spacecraft goes off, but second of all, because it takes a lot more energy to get up to that speed. So this right here, this part of the equation, is actually the part that you would use in your high school physics class to figure out, masses on Earth and at much, much less than the speed of light. This is just the normal kinetic energy equation. It's 1/2 times the mass times the velocity squared. So if you're moving 1 meter per second, the mass is 1, or let's say the mass is 2, and the velocity is 2. So you'd have the mass is 2, the velocity is 2 squared, and I remembered the parentheses this time. So we would have 2, I accidentally, there we go. Hello. So we have, if you hit the thing, it goes to the next thing, and I have to do it the right way. So we have, there we go. Go back. So if you have, no, not going to do it. Not going to do it. Okay, so anyway, if you guys get it. So if you have 1/2 mv squared 4 times 2 is 8, 1/2 that is 4. So your kinetic energy would be 4, in that case. However, if you add relativity in, you got to add this little part here. This section right here is what they call the relativistic adjustment. I won't derive that, but you'll notice it looks a heck of a lot like gamma. The difference is you've got this -1 here. So if this is 0, and you've got 1 over 1 minus 1, then this whole thing tends to be 0 at lower speeds. So you don't get a lot of relativistic effect. And by the way, this is the rest mass times the speed of light squared. So the speed of light is pretty fast. We're going to, for all intents and purposes, we're going to say that it's 300 million kilometers per second. It's a little less, 2997. And if we square that, it's a lot. So let's look at that. I actually did this. So let's imagine our spaceship. I did a little article on this where I took our mass up to a tenth the speed of light and ignored relativity, because you could at a tenth the speed of light. But let's take it up to a gamma of 10, 0.995. And I wanted to figure, what is the smallest ship that I could live in for 4 years traveling to a distant star system? And I figured that a 757 was a good thing. And I looked up how much a 757 was, and it weighs about 100,000 kilograms, a 757. You guys, it's 242, I think is the number of seats. It's a big aircraft. It's not a 747, But it's a nice, comfortable aircraft. They've got good things in the seats. So I think I could live for 4 years in a space the size of the interior of a 757. So let's do the math. First of all, let's figure out the regular kinetic energy part, that part. That's easy. We just go 1/2 mv squared. So here's the weight of our ship. Here's the speed of light. I actually took the actual speed of light, 2985000. We're doing it just for accuracy's sake, but it doesn't really matter all that much. And divide that by 2, because it's 1/2 right here. And we get 4.45 times 10 to the 21 kilogram meters per second squared. That's the amount of energy, kinetic energy, from the normal kinetic energy that you get when you're traveling at this 0.995% the speed of light. Oh yeah, by the way, this is 0.9. I'm going to undo that. Hold on. This is 0.995% the speed of light. This value right here. And that value is in a unit called joules. So I used a handy-dandy tool called Google, and I looked up total amount of energy human beings used in 2024 in joules. And someone had actually done the computation. And here's what they came up with. Human energy usage in 2024. 4 times 10 to the 20th joules. Now you'll notice that this is 10 times the total human energy usage in 2024. I'm talking everything. I'm talking transportation, electricity, AI servers filled with NVIDIA cards. You know, that's a lot of energy that human beings are using. And to get a 757 up to a reasonable relativistic speed where we can actually take advantage of time dilation, we need to use 10 times the human energy usage. But wait, there's more. We forgot about this part. This is the relativistic adjustment. So let's add that to the mix. Here's the relativistic adjustment, and I'm going to fill in all the figures. By the way, we know that this is 10 because we've chosen gamma to be 10. So 10 minus this 1 is 9. So we don't have to do the calculation of that part. We just have to multiply all of this by 9. It's real simple. Very easy to do because we've already picked gamma ahead of time. Gamma's 10. So we end up with the speed of light here, which is 300 million meters per second. The weight of the spacecraft, which is 100,000 kilograms, just arbitrarily picked because of that type of airplane. And we get 8.1 times 10 to the 22nd joules. What you'll notice is even more than the kinetic energy value, the regular kinetic energy value. So we can almost discount this, because this is 1/20th of this. So just getting roughly in the ballpark, let's take a look. We get 8.1 times 10 to the 22nd. And human energy usage, compared that, 4 times 10 to the 20th. So how much more? That actually equals 200 times the total human energy usage in 2024. So getting to the stars in a reasonable period of time is technically possible. But look how much energy you have to do it. And now this is assuming that we have a massless source of energy. So let's go one step further and figure out, let's say we have a perfect source of energy. And I'm not going to derive this. I could, but I'm not, because I don't have enough time. E equals mc squared. That's another outgrowth of the paper. It's actually never written out as such, E equals mc squared. He writes it out in words in it. Later on, he did another little paper where this kind of comes out growth, and it's actually not complete. There's actually a few other things added on at the end. But this is a good estimate of the amount of energy you can get out of an object at rest mass. This m is the rest mass of an object, so 1 kilogram speed of light squared. So let's figure out, using this equation, how much mass we would need to convert entirely into energy in order to get our spaceship up to speed. Now, we do have, it's not an outrageous amount of mass. It's actually a pretty, this E equals mc squared is pretty powerful. The problem here is, in order to get that out, you need to take all of the mass and convert it entirely into kinetic energy. When you create nuclear fusion, you're getting like 0.07% of the energy out of hydrogen when you create hydrogen into helium, for example, in the sun. It's a very small amount of the energy. So we're not getting all of the energy out of fusion on Earth. But if you take a photon, or a proton and an antiproton, you guys all know from Star Trek what happens when you take a particle and its antiparticle and you slam them together, you get energy, completely converted from mass into energy. Proton, antiproton, put them together, completely obliterates them. Or they fight until death. Yeah, they fight each other for all time. So let's just assume we've got a nice tub full of antiprotons and another nice tub full of protons on our ship, and we have the ability to do this. Now we're going to have to make those protons. We're going to have to use 200 times the entire human consumption of energy in 2024 to make them to begin with, but we do it. We'll just assume that we do it. So we need to get this amount of energy out. We've decided that that's the amount of energy. I'm forgetting the kinetic energy because that's peanuts. So we need the mass times the speed of light squared. So the mass times 9 times 10 to the 16th. We take and divide both sides by this, 9 times 10 to the 16th. So we bring this down here. So 8.1 times 10 to the 22nd divided by 9 times 10 to the 16th equals the mass. And our mass works out, if we're dealing with joules, to 900,000 kilograms. Now, if you'll remember, our airplane was only 100,000 kilograms. Yes?
Do you want to slow down?
Do I want to slow down?
Yeah.
Presumably. Presumably you want to slow down, yes. Presumably you want to slow down. So here's the thing. That's a really good point. You do want to slow down when you're doing this. So here's the thing. You have to take at least 900,000 kilograms of matter with you, or scoop it up in between the stars, which actually turns out it's much more difficult than you think, because as you get faster and faster, those things hit you, and you have to push harder into them. So, in other words, instead of a 100,000 kilogram spaceship, you need a 1,000,000 kilogram spaceship. And because you have a 1,000,000 kilogram spaceship, you need even more energy to get up to that. So in other words, instead of 200 times the total energy consumption of humanity, it works out to something like, it is a ridiculous amount of energy. Now, it's possible, but it's not really probable. And so for me, there's a really interesting question that people have proposed since we started thinking about life in the universe. One of the big questions is, why aren't they here?
That's the reason.
This is the reason, I think, because it is really, really expensive. Dilithium crystals. So in other words, no aliens. because, wow, it takes it takes a big expense to get across the universe. Technically, it's possible, but it's not going to happen anytime soon unless we figure out a way to generate a lot more energy, which is why we need to build a Dyson sphere around our star.
Someone would probably try to deport me.
Yeah, that's true. Yeah, they're alien. So anyway, I'm not going to derive E equals mc squared, but it's actually really interesting how it comes about. Comes out about as you can actually figure it out by virtue of the Doppler shift. It's kind of cool. But any questions? Yes.
So instead of sending you in your 747, what if we miniaturize the information of you and accelerate that?
Yeah, that'd be easier.
A lot less energy.
Yeah, if you wanted to be beamed, you could do it with a minimal amount of energy because photons, light, is massless. And just conveniently, it travels at the speed of light. So you'd have to, wait 40 years for us here on the ground to get there, but you would get there as fast as humanly possible, or as fast as physics will allow us to go. Yeah, assuming that you could send information on how to reconstruct yourself at a remote location, then yes, you could get to the universe that way. Who knows if that's actually going to be you? That's the subject of a lot of Star Trek episodes. Is the copy of you you? I don't know. Yeah, any other questions? Yeah.
I'm just now remembering, I can't remember the actual name of it, but you will know it immediately, but the idea of sending a really tiny probe
Yes.
with lasers.
Yeah, you can. Okay, so another thing, to send another tiny probe, this is a really, with a light sail, you could actually do that. However, to get it up to the speed of light, it would still, even that little tiny mass would still be quite a lot. Plus, you would have to collimate the laser such that it would have to follow that ship until it got up to the speed of light. That would be exceptionally, the technical challenges for that are very difficult. Yes, you could, in fact, send a very, very tiny probe. I'm assuming that we squishy human beings want to actually travel to the stars. I do. I would love to go to Alpha Centauri or something like that. But yeah, it's very difficult to do. But yes, we could send a light sail, fire it off, get it up to close to the speed of light using a laser beam to push it.
You wouldn't have to worry as much about relativistic, you wouldn't have to be fast. You could go, say, 0.8. It still would require a certain.
Yeah, from our point of view here on Earth, this is the assumption is that we ourselves want to go. Yeah, so yeah, if you want to get a probe there, then yeah, it's possible to send a probe to another star system. Do that. And we could probably still take a long time. Yeah, I mean, 0.8% the speed of light to get to Alpha Centauri would be 4.4 years or something like that.
Our time would be the unaltered time.
Yeah, yeah. So, anything else? Did that explanation help? I mean, I know I was a little tongue-tied when I was actually doing the math because I've never done a math in front of an audience. But did it kind of make you understand how simple the math is?
Yes.
Yeah, it's actually quite simple. It's just a matter of throwing away the idea of the luminiferous ether and figuring out what the universe looks like when you take those two postulates. The speed of light is the same in all inertial reference frame, and there is no preferred reference frame. You can't tell which reference frame you're in by conducting an experiment. So all reference frames are the same. So anyway, guys, I appreciate you hanging out with me, and thank you so much. I appreciate it.
And she said, "Oh, I've got a date. Some guy met on the internet. He's a French model, And this guy walks up, this big, sort of galumpy-looking guy. He's tall and overweight, And he says, bonjour, but he's not French. So anyway, I guess that about wraps up the program. So unless anybody's got any questions or whatever, what's that?
to 747. Oh.
Oh. So, anyway, we'll hope for a clear night where we can, do some actual observing.